Good day, everyone. I'm Efrelin Joel Chofilo from BS Ed Math 3B. 6-3, the central limit theorem. In addition to knowing how individual data values vary about the means for a population, statisticians are interested in knowing how the means of samples of the same size taken from the same population vary about the population mean. Distribution of sample means. Suppose a researcher selects a sample of 30 adult males and finds the mean of the measure of the triglyceride levels for the sample subjects to be 187 milligrams or deciliter. Then suppose a second sample is selected, and then the mean of that sample is found to be 192 milligrams or deciliter. Continue the process for 100 samples. What happens then is that the mean becomes a random variable and the sample means 187, 192, 184 up to 196 constitute a sampling distribution of sample means. So what is a sampling distribution of sample means? A sampling distribution of sample means is a distribution using the means computed from all possible random samples of a specific size taken from a population. If the samples are randomly selected with replacement, replacement means that the data can be repeated. The sample means for the most part will be somewhat different from the population mean mu. These differences are caused by sampling error. Sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. We must acknowledge that even the best random sample will always be a little different from the true population. As your sample size increases, your sampling error decreases, but increasing your sample size also increases cost, both time and money. When all possible samples of a specific size are selected with replacement, the distribution of the sample means for a variable has two important properties. Properties of the distribution of sample means. First, the mean of the sample means will be the same as the population mean. Second, the standard deviation of the sample means will be smaller than the standard deviation of the population, and it will be equal to the population standard deviation divided by the square root of the sample size. The following example illustrates these two properties. Suppose a professor gave an 8-point quiz to a small class of 4 students. The results of the quiz were 2, 6, 4, and 8. A. What is the population mean and the standard deviation of the population? So to solve for the population mean, just add all the numbers in the population. We have 2 plus 6 plus 4 plus 8 divided by the population size. Since we have 4 numbers, therefore divided by 4. So the population mean is 5. And to solve the standard deviation of the population, we have this formula, and I'm going to use a table for us to understand the distribution. For the first column, we write all the values of x, so we have 2, 6, 4, and 8. For the second column, we have x minus mean. In each row, we need to subtract the value of x to the population mean. So for the first row, we have 2 minus 5 is equal to negative 3, 6 minus 5 is equal to 1, 4 minus 5 is equal to negative 1, and 8 minus 5 is equal to positive 3. For the last column, we need to square all the values of x minus mean. So we have negative 3 squared is equal to positive 9. 1 squared is equal to 1. Negative 1 squared is equal to positive 1. And 3 squared is equal to 9. So the summation of x minus mean squared is equal to 20. So to solve the standard deviation using this formula, substitute the values. So we have sigma is equal to square root of 20 divided by 4. We got 5. And then the square root of 5 is 2.236. So the standard deviation of the population is equal to 2.236. So this is the graph of the scores of the student in their quiz. This is called uniform distribution, a type of probability distribution in which all outcomes are equally likely. Now, if all samples of size 2 are taken with replacement and the mean of each sample is found, the distribution is shown below. Since the size is 2, so the sample below are listed in size 2. And since it is with replacement, so we have repeated numbers of data like 22, 44, 66, and 88. After that, we have a frequency distribution of sample means to get the numbers of items in the sample. Using the formula mu of x is equal to the summation of sample mean over n, substitute the values, so we have mean of sampling distribution is equal to 80 divided by 16, that is 5, which is the same as the population mean. Hence, mu of x bar is equal to the population mu. As we can see here, the standard deviation of sample means denoted by sigma of x bar is equal to 1.581, which is the same as the population standard deviation divided by square root of 2. So, sigma of x bar is equal to 2.236 divided by square root of 2, we got 1.581. Note, rounding rules were not used here in order to show that answers coincide. In summary, if all possible samples of size n are taken with replacement from the same population, the mean of the sample means, denoted by mu of x bar, equals the population mean mu, and the standard deviation of the sample means, denoted by sigma of x bar, equals to the population standard deviation all over the square root of n. The standard deviation of the sample means is called the standard error of the mean. Hence, the standard error is equal to the standard deviation over square root of n. A third property of the sampling distribution of sample means pertains to the shape of the distribution and is explained by the central limit theorem. So what is central limit theorem? The basic idea behind the central limit theorem is this. Let's say we collect samples of size n from a population, calculate the mean of each of those samples, and plot those means on a histogram. The histogram will approximate a normal distribution. So let's say you have 100,000 people in a town, and you choose a sample of 30 individuals, and then you calculate. You calculate the mean age of the 30 individuals. So sample 1, let's say, is 41.8. And then the mean of another 30 individuals is 39.6. And then take another sample that is 41.5. Repeat this process. And then if you plot all this on a graph, the graph will have the shape of a normal distribution. Even if the graph population we don't know, even if it's not normal, this graph where we plot all of the sample means or the means of each sample. So this will be x bar. It will have the shape of a normal distribution. So that's the gist of the central limit theorem. If the sample size is large enough, the sample distribution, take it from any population distribution, regardless of its shape, will approximate a normal distribution. Value if n is equal to a greater than 30. So, let me illustrate that with some example. On the left, we put population distribution, and on the right, we have the shape of the sampling distribution. So, let's say our population distribution has the shape of a normal distribution with mean mu, and the random variable is x. Now, if we collect samples out of this population and calculate the mean of those samples and then plot it on a graph, we're going to create a new distribution called the sampling distribution, but specifically the sampling distribution of the sample means, because we calculated the mean of each sample taken from the population. So this gonna be x bar because we're plotting the means of each sample on this graph. So since the population distribution had the shape of a normal distribution, the sampling distribution will also have this shape. But for this case, for any n value. The reason why is for any n value is because the population distribution already has the shape of a normal distribution. But now, what if the population distribution have a different shape? For example, you have a shape of a uniform distribution or a shape of an exponential distribution, or if you have shape of just unusual distribution. If we collect samples from the population, calculate the mean of those samples and plot on a graph, we're going to have the sampling distribution of the sample means. And if n is large enough, let's say it is greater than or equal to 30, then the sampling distribution will approximate a normal distribution. So in this case, if the population distribution has a shape other than a normal distribution, you need to collect samples with a large enough size, 30 or more. The larger the sample, the better approximation will be. Now, since the sampling distribution approximates the shape of a normal distribution according to the central limit theorem, we could use the z-table to make some probability calculations. But before that, here are some symbols and variables that you need to know. Mu is the population mean. X bar is the sample mean. Mu with a subscript of x bar, this is the mean of the sampling distribution. Sigma, this is the standard deviation of the population. Sigma with an x bar as subscript is the standard deviation of the sampling distribution. So here are the formulas to remember. So for sample standard deviation, that's the population standard deviation divided by the square root of sample size. For z-score formula, z is equal to the sample mean minus population mean divided by the sample standard deviation. Problem number 1. Hours that children watch television. A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. First, let us solve for the sample standard deviation. So to solve the sample standard deviation, let us use this formula. Then substitute the values. So we have sigma with an x bar as subscript is equal to 3 divided by the square root of 20. We got 0.671. So since the variable is approximately normally distributed, the standard deviation of sample means will be approximately normal, with a mean of 25 and standard deviation of the sample mean is 0.671. So to find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. Sample mean is equal to 26.3, population mean is equal to 25, sample standard deviation is equal to 0.671. Using the z-score formula, substitute the values. We have z is equal to 26.3 minus 25 over 0.671. That is 1.3 divided by 0.671. We got 1.94. To find the area of 1.94, we can use the z-table. Let us find the first two digits down to the left corner of the table, which is 1.9. Then look at your hundredths place, which is 0.04. You'll find that across the top. Then the intercept number of that column and that row is 0.9738. Now, that value we look up is the not shaded area of the curve. But we're looking for the area of greater than 26.3. Remember, the area underneath our curve is 1. So we subtract 1 by 0.9738. We got 0.0262 or 2.62%. So the probability of obtaining a sample mean larger than 26.3 hours is 2.62%. Example number 2. The average age of a vehicle registered in the United States is 8 years or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that the mean of their age is between 90 and 100 months. Since our sample size is 36, that is greater than 30, therefore the sampling distribution of sample mean is approximately normal. First step, let us identify the given. So we have here mu is equal to 96, sigma is equal to 16, n is equal to 36, and we have two sample means, 90 and 100, because it is between 90 and 100. Then, plot the values. Next step, convert the two sample means into z-score using this formula. Then, substitute the values. So, z sub 1 is equal to 90 minus 96 over 16 divided by the square root of 36, that is equal to negative 6 divided by 2.667. We got negative 2.25. For z sub 2, we have 100 minus 96 over 16 divided by the square root of 36, that is 4 divided by 2.667, we got 1.50. To find the area between the two z values of negative 2.25 and 1.50, look up the corresponding area in table E and subtract one from another. The area for z sub 1 is equal to negative 2.25 is 0.0122. Then the area for z sub 2 is equal to 1.50 is 0.9332. Hence, the area between 0.9332 minus 0.0122 is equal to 0.9210 or 92.1%. So the probability of x bar is greater than 90 but less than 100 is equal to 92.1%. Students sometimes have difficulty deciding whether to use this z-score formula or this. The formula z is equal to x bar minus mu over sigma divided by the square root of n should be used to gain information about a sample mean as shown in this section. The formula z is equal to x minus mu over sigma is used to gain information about an individual data value obtained from the population. Notice that the first formula contains x bar, the symbol for the sample mean, while the second formula contains x, the symbol for an individual data value. Meat consumption. The average number of pounds of meat that a person consumes per year is 218.4 pounds. Assume the standard deviation is 25 pounds and the distribution is approximately normal. A. Find the probability that a person selected at random consumes less than 224 pounds per year. Since the question asks about an individual person, the formula z is equal to x minus mu over sigma is used. Substitute the values. We have 224 minus 218.4 over 25. That is 0.22. The area to the left of z is equal to 0.22 is 0.5871 or 58.7%. The probability of x is less than 224 is 0.5871. B. If a sample of 40 individuals is selected, Find the probability that the mean of the sample will be less than 224 pounds per year. Since the question concerns the mean of a sample with a size of 40, the formula z is equal to x bar minus mu over sigma divided by the square root of n is used. Substitute the values. We have 224 minus 218.4 over 25 divided by the square root of 40. We got 1.42. The area to the left of z is equal to 1.42 is 0.9222.